So let's move on then to do the energy equation. Okay, so energy equation. Let's see, what do we need here? We have, over here is our energy equation that we came up with before. So some things we need here are what? So we need to say, we have this dt dx appearing, or dt dy. In order for us to decide how or what that dt is, we have to come up with maybe some reference temperature, right? Or reference temperature difference. We never want to think about like an absolute temperature is important here. We're talking about a temperature difference. So for this problem, we'll just call whatever that temperature difference is, we'll call that delta T. And so that delta T might be a difference between a surface temperature and the free stream temperature, something like that. So we'll do the normalization in terms of delta T, or the order analysis in terms of delta T. So let's start here. Okay, we have this first term is rho times C times U infinity times our temperature difference delta T divided by L. This term is rho C V sub delta times delta T over, not L, over delta, right? That's dt dy. Okay, this term is going to be, let's see, we have K in front, we have delta T, and it's the second derivative, so then it's over L squared. This term becomes K delta T over delta squared, because it's dt dy squared. And then the last one is, let's see, mu in front, and then we have, let's see, U infinity squared over delta squared. Let's see if I did that right. Yeah, right, because now, okay, so the last one, don't get confused by that. We have, everywhere we see a second derivative, we have the second derivative being the quantity over the thing in the denominator squared. Here we have the entire derivative is squared, right? So that's why we have U infinity squared over delta squared. Any questions on that part? No, okay. So going through this, let's see, what are we gonna do here? So we can see that by inspection, the U infinity or U velocities are much bigger than the V velocities, right? We know that's true. So we'll keep that in mind as we're going through. So let's see what we can do for the order here. So it turns out that if you look at it, this one here and this one here actually have the same order, because let's see if I can kind of highlight it here. So this ratio here, U infinity over L, is the same as this ratio here, V delta over delta. So even though they're sort of different by orders of magnitude, the ratio of them is the same. Okay, so these end up being about the same order. Let's see, and then this would be, so this one here, we're going to take again and divide this through by some normalizing thing. So we're going to actually take this and divide through by rho C U infinity times delta T over L, which is our first term that we decided was the same there. So with that, we get K times delta T over L squared times L over rho U infinity C delta T. Dividing through by rho U infinity C delta T. Okay, if we do that, then we end up with, this becomes, let's see, we have K over rho C, that's alpha. We have alpha appearing, it's an alpha, divided by L, U infinity in the denominator. And then in order to get something kind of useful out of this, let's multiply by kinematic viscosity over itself. So nu over nu. Okay, so now we can see that this actually becomes 1 over Reynolds times Prandtl. If we can see that. Right, alpha over nu, or nu over alpha is our Prandtl number. Rho U infinity L over mu, which is U infinity L over kinematic viscosity, that's our Reynolds number. Okay, so this term is on the order of 1 over Reynolds times Prandtl. Okay, so then let's see this one, I'm totally running out of room here, but this one here, we do the same thing and we're going to divide through. We end up with, I'll just kind of give you the result here. This one ends up being also 1 over Reynolds times Prandtl, but it's also L squared over delta squared. Right? That's what that ends up being. Again, you can apply that momentum boundary layer sort of relationship, and this ends up being, pretty much close to 1. All right, let's see. And then the last one, let's see the last one here. What do we do with that one? Yeah, so the last one here, if we go through this analysis, the conclusion is this ends up being, let's see, yeah, well, if we just look at it, right? So U infinity squared over delta squared. So we have mu times U infinity is a large number, delta is a small number. So this is going to have to be significant, right? So we have to keep this, keep that. So what did we do here? We went through and basically decided that, what, can we get rid of anything? We have dTd, u dt dx, v dt dy, k dt dy, right? So this one here, oops, what just happened? This one here ends up being a small number. So we can get rid of that one term, right? And our final result ends up being rho c u dt dx plus v dt dy plus, or sorry, equals k d squared t dy squared plus mu du dy squared. So that's the end result of going through this whole thing, right? We end up with a somewhat simpler energy equation. All right, so unless there's questions on that, let's look at the summary here, right? This hopefully is a little cleaner, but it shows that after this whole kind of tedious analysis we've gone through, decided that we could throw away certain things. And the really valuable thing, I think, is one, there's just a couple terms in the energy and x momentum, but we can also decide that the y momentum is basically not important. So now we have this system of equations that gives us the energy and flow in the boundary layer. Right? This is still not especially simple. Right? We still have some things going on that we have to deal with, but at least it's a step in the right direction.